Experiment 11, the determination of solution concentration via visible spectrophotometry or spectroscopy. As always, I have on my nice clean gloves, I got on my lab coat so I don't get holes in my shirts, and I got my lab goggles on, of course. I probably shouldn't be wearing the Fitbit, but it makes my mother happy to know that I walk more than 7 miles a day. So here we go. I have obtained 6 cuvettes. Notice, if you can, that there is a frosty side of the cuvette and a clear see-through side to the cuvette. An opaque side that light really doesn't get through very well, and a perfectly transparent side that light does get through very well. It's important that you pay attention to that because if the light can't get through, that kind of defeats the entire purpose of the experiment, because we are measuring how much light gets through blue copper sulfate solutions, and if the light can't get through the thing that the solution is in, the experiment doesn't work. So we have our visible spectrometer, it says right there, which means that this thing can be set to various wavelengths of light, but in the visible region of the spectrum, which is generally assumed to be about 400 to 800 nanometers. A nanometer is 10 to the negative 9th meters. And the reason that we use nanometers for this is because it makes for nice round numbers. Instead of saying like 0.000000004 meters, we have 400 nanometers. Now, if I can angle this thing just right, you can see that the light bulb is at the bottom of this, and that means that the light is shining that way. If I turn it this way, there's no light bulb, okay? Light traveling this way does not exist. So it's important that when we use our spectrometer or spectrophotometer, that we put the see-through side, the transparent side, facing this way. We want to always handle our cuvettes by the frosty side so that we don't scratch up or get fingerprints on, although that would be hard with gloves, on the transparent side. So really, really, really important handling these things. Now these are brand new. They just gave them to me out of the box, so they're not squeaky clean. A lot of times in the lab they're scratched up, and so you have to do something called matching your cuvettes, which is to put all 6 of them into the spectrometer and make sure that they give you the same value. Because the fundamental basis of this experiment is that every single thing is the same from cuvette to cuvette to cuvette, except for the blue solution in it. Okay, the wavelength of light is the same, the cuvette has got to be exactly the same. Everything has to be constant except for the concentration of the known solution. You cannot really determine the concentration of something that is unknown. I mean, there are ways of doing it, but not this technique. Okay, we have to know what it is that we're looking for so that we can set up what is called a calibration curve, where we have known concentration, known concentration, known concentration, known concentration, and according to Beer's law, the simplest equation in chemistry, A equals ABC, big A, absorbance of light, is directly proportional to little c, the concentration of your solution. So the more concentrated, the darker the solution, the more light is absorbed. You've experienced this in your everyday life, but this is quantifying it, putting a mathematical equation with it. That if we have more stuff, it will absorb more light. What that means to your eyes is it looks like a darker solution. All right, so I have my 6 cuvettes. I have a 10 milliliter graduated cylinder, and I have my 4 Erlenmeyer flasks that I will put my known concentration solutions in. All right, I need some deionized water, which I have on another cart. As always, it says distilled water, but it is deionized water, and so we have that at the ready. So I am going to get my from the stockroom solution of copper sulfate, which should be exactly what it says on the bottle. We're going to assume that it is 0.1 moles per liter. 0.1 moles of copper sulfate per liter of solution, and it's in this bottle. Now there are some chunks at the bottom, so I'm a little bit skeptical of this concentration, but as long as I make my solutions carefully, the entire experiment will be off, and I'll still be hopefully internally consistent. So in step 2, it says get 10 milliliters of the standard solution from the stockroom of 0.1 molar copper sulfate. I need to get exactly 10 milliliters. So we'll see how good my pouring skills are this morning, or if I need to go get a pipette and remove some. Down at eye level to be able to see the meniscus perfectly. Oh, spot on. Spot on. Until this drop that was stuck to the side comes down. Now I am, in fact, a hair over, and will need to get a pipette to remove some. So I have a pipette, and I will very carefully remove that extra drop that came in so that my meniscus is exactly on the 10 milliliter line. All right, and then I will pour 5 milliliters of it into Erlenmeyer flask A. It says put all 10 in there, except then it immediately says take 5 of it back out and put it into Erlenmeyer flask B. So I might as well just take the 5 milliliters out, put it in A, and leave 5 milliliters in the graduated cylinder, since that is the next step. If you read your instructions before you accomplish them, sometimes you can save yourself a little time and do things in a little more logical way for you. Now just a word on graduated cylinders. Oh, spot on. And versus flasks. It looks like, if you look at this flask has around 5 to, or actually close to 10 milliliters in it. A flask is not a precision volume measuring piece of glassware. A graduated cylinder is. These can be plus or minus 5 to 10%. I think it even says on it. Yeah, this one says right on it. Plus or minus 5%. That's not close enough, okay? You never use a flask to measure exact volumes. You use it to measure approximate volumes, but not exact volumes. So I have now 5 milliliters of my solution in A, and I know its concentration is 0.1 because it's exactly what I took out of my original bottle. Now I'm doing a process called serial dilution, and I am taking 5 milliliters of the 0.1 molar solution that I started with, and I'm going to add approximately 5 milliliters of water, although it's technically enough water to make 10 milliliters of solution. Now, since I have a squirt bottle here, I'll be able to do this really precisely and get exactly 10 milliliters total solution in here. And what I will have done then is to cut my concentration in half. And I will pour this new 10 milliliter solution that has been diluted in half into Erlenmeyer flask B. And I'll give it a swirl, 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 swirl. Because I want it mixed really, really, really well. Even though I'm going to put 5 milliliters of it back in here, I can't do what I did the first time by just leaving it in here, because I want to make sure that my solution is stirred and mixed really, really, really well. So I have now my solution B that has been 0.1 divided in half, so 0.05 molar solution. And I'm going to put 5 milliliters of it back into my Erlenmeyer flask, into my graduated cylinder. Learning the names of things is a skill that you develop in this class. That's useful on the job, because when you get hired for a new job, you got to learn what stuff is called. All right, so I overshot a little bit, which is fine, because I have my pipette, and I can just suck out until I get down to 5 milliliter line. Exactly. All right. And solution B is complete. And I have 5 milliliters of solution B now in my graduated cylinder. And I will get my deionized water and go back up to the 10 milliliter line. Now there's another alternate way of making these solutions, of stirring them and using it only in the graduated cylinder here, and that would be, maybe I'll show it to you this time. Your instructor might have thought of this, is that I can take my pipette and I can squirt the air out now so I don't splash, stick it in the graduated cylinder and mix it this way, just by sucking it in and blowing it out. That, like 20 times or so, is just going to be just as good as putting it into the Erlenmeyer flask and stirring it in that. So I actually like this way a little bit better. To me, it's more convenient. I don't have to pick up the graduated cylinder and potentially spill it. So now I'm going to take 5 milliliters out and put it into C. See, even though I wrote the lab manual, there are things about it that when I get into the lab, I like to do a little bit differently. Maybe I'll change it for the next edition. All right, there's exactly 5 milliliters, although the volume, honestly, doesn't really matter. I mean, I don't need 5 milliliters in here. It's not going to fit into the cuvette. But making the solution exactly 5 milliliters of B plus the 5 milliliters of water or so that I have 10 milliliters total solution, that's important. All right, so I've got solution C, which is half of 0.05, so 0.025 moles per liter. And I have 5 milliliters of it in the graduated cylinder. Last time, I'll add enough water. Again, it's around 5 milliliters, but saying that I'm adding 5 milliliters is technically incorrect. Until I have exactly 10 milliliters total solution, and then this time there's no reason to use the pipette. It's the last dilution that I'm doing. I'm just going to pour it straight into Erlenmeyer flask, letter D. And swirl, 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 swirl. It's not a solution until it's been mixed. There's a saying in emergency medicine, when I was an EMT, that you're not dead until you're warm and dead. You know, you find somebody in a body in a frozen river, you can potentially revive them. So they're not dead till they're warm and dead. It's not a solution until it's been stirred. There's a lab that I used to do at a different school, and the students would add some solid into a bottle, pretty much like this bottle. They would add some solid into the bottle, and they would add water, and they would leave it for 2 weeks before they would use it. And then they would come back and use it, and they would find that there was no solid dissolved in it. And they'd say, well, how come? And I'd say, because you didn't stir it. All the solid was dissolved at the bottom of the bottle, and it just had never mixed its way to the top, just because it was sitting in a cabinet still for 2 weeks. Shaking your solution, stirring your solution somehow, either with a stirrer or just swirling it or whatever, is really, really, really important. Okay, now what I want you to see, and hopefully the camera will pick this up, is here is my original solution, which should match solution A. And it does, all right, if you can see it in there, all right? Just by inspection, A is darker than B, which is darker than C, which is darker, and I don't even know if you'll be able to see the color in this, than D. We can eyeball it. Our eyes are great spectrophotometers. So we can, when we get to our unknown, I'll just choose one at random over here. That bottle is empty. Useful. Here we go. Unknown number 17. Did they spell unknown right this time? Yeah. Unknown number 17. When I put it in the cuvette, let's see if our eyes can be our spectrometers even better than the instrument. Let's see what it says. All right, so we are up to step number 6. I've obtained a spectrometer and I've turned it on. I've already set my mode to data matrix. Is the cord long enough for you to see this? Let's see. All right. Let's tilt. I have set it to data matrix. I have set my wavelength to 800 nanometers. And so here is a big question. If the visible spectrum is from 400 to 800 nanometers, And you should have already gone over this in class, but let's discuss for a second. There is ultraviolet on one end of the visible spectrum and infrared on the other end of the visible spectrum. Ultraviolet can break bonds. It's very high in energy. Then comes visible light. Then comes infrared, which only can make molecules kind of make the bonds in the molecules vibrate. Excuse me. So much lower in energy, infrared. So the red end of the spectrum is the low energy, and the violet end of the spectrum is high energy, 400 to 800 nanometers. Short wavelength is high energy. So that means that the 400 end is the violet end, and the 800 end is the red end of the spectrum. If the 800 end of the spectrum is the red end of the spectrum, the low energy end of the spectrum, how come for our blue solutions we have our spectrometer set for 800 nanometers? The reason is because we are measuring the absorbance of the solution. And a solution which looks blue isn't absorbing blue. It's absorbing red. And so we set our spectrometer for the red wavelength of light to see how much is making its way through. Now, if you look at a blue light, that thing is emitting blue light into your eyeball. So that is the 400 wavelength, right? The blue light is hitting your eyes. This thing looks blue because it's absorbing red. White light is hitting it. The lights in this room are white, if you want to see, right? White lights in the room. And the white light is all wavelengths. The red portion of that white light is being absorbed by this solution. The blue is not being absorbed, and that's why it appears blue. We want to check out how much red light is being absorbed by these various solutions. So I'm going to take all 6 cuvettes one at a time, and I am going to match them. I forgot that I put that step in here. So frosty side I'm hanging on to. The transparent side is facing towards the camera, and I have my spectrometer set where the light is going this way, you remember? And so I'll take a reading in the spectrometer, and it's reading out no absorbance, which is strange because it should be doing something. Oh wait, we got to calibrate first. So let's calibrate it empty, even though we'll have to recalibrate it later. So we're going to skip our warm-up. There's just a little warning screen on there, and finish the calibration. Just takes a second. Okay. All right. Now we see that the screen is changing a little bit. So when I put this in, I should get it a reading. All right. So not much absorbance just by the spectrometer. Let's get the glare off. Come on, no glare. 89, 90, somewhere in there. 0.089, 090. Let's make sure all 6 are the same right out of the package. Again, only touching the frosty side, putting it with the transparent side facing 0.1, close enough. $84, close enough. $73. All right, we're 0.2 different from where we were to begin with. But okay. 0.02, yeah. 83, same as one of the other ones, exactly. 80. All right, so all 6 of these cuvettes are pretty close to this exact same absorbance. Now, if we were doing really precision measurements, we might want to swap out that one that was down in the 70s, but close enough for our work. Now, just another word on these cuvettes. These are made out of plastic. They cost about 2 cents a piece. There are ones that look exactly like this that are made out of something called single crystal quartz that cost $600 a piece, exactly the same size, 1 centimeter across, $600 a piece. My suggestion, and again, this is a translatable skill to any new job, is to treat it as if it costs $600 a piece. Right? Treat your equipment carefully so that your boss can pay you instead of replacing equipment. Okay? All right. Now, place all 6 cuvettes. We made sure that they were the same. Some of the cuvettes are not square like this. They have a short end and a long end, and if so, you need to consult the lab manual and see what that one looks like. These are just square cuvettes. You want to make sure that the cuvette is placed in the spectrometer so that it would go through the long way, the 1 centimeter way. There, it's only 1/3 of a centimeter in the opposite direction on those cuvettes. But these are 1 centimeter in both directions. However, they have a frosty side and a transparent side, so you got to make sure that they always go in the right orientation. Okay, so we're going to put a solution from each Erlenmeyer into its individual own cuvette. We're going to have one with water, and we're going to have one with our unknown, which is why we have 6 cuvettes. So I'm going to arrange these guys where hopefully we can get everything on screen and I won't knock it over. I got A, I got B, I got C, I got D, I got water, and I got my unknown number 17. So actually let's swap these around. Here we go. All right, so water first. I'm filling these about 2/3 of the way up. You can see the water level is right there. Just because, you know, when the cuvette is in there, the light beam is not going to go up to the top. This actually just goes straight through. I don't know if you can see the cuvette is just dropping through and sitting on the table. Magic trick. Whoa, it's coming out the bottom. It's got to sit flat on the table. The light's going this way. My transparent side will go that way, only holding onto these from the frosty side. And I have my water cuvette ready to rock and roll. Next, unknown. I'm going to use this. Ooh, might have to switch unknowns. That sucker is stuck. Things that make you go, Yeah, that dropper is completely fallen apart. So, no unknown 17 for us. No empty bottle 1 for us. We will grab a different unknown. That's an empty bottle. That's an empty bottle. Empty bottle. Wow. Empty bottle. Someone is messing with me today. Full bottle. Unknown number 16. Let's see if the stopper functions on this one. No. The stopper is trashed also. Let's see if I can manage to get it out without spilling the bottle all over myself. Ingenuity. All right. Swirl, swirl, swirl. Unknown number 16 into the cuvette, about 2/3 full. Probably get away with half or 1/3 even, but just so that we're confident. Okay. Unknown. There. D. Could use a pipette for this. I think I can pour it carefully enough. D. C. Only touching the cuvettes on the frosty side. The opaque side. The not translucent side. B. Glad that cuvette was empty. A. All right, and here we go. Making the solutions is what takes the long time in this lab. Getting a stopper that functions in the unknown can apparently take a long time in this lab. Measuring your different concentrations, no time, as you'll see in a second. We will put the water in. Again, all we care about is the absorbance of the blue copper sulfate. We don't care about the absorbance of the cuvette. We don't care about the absorbance of the water. Important point, we don't care about the absorbance of the water. So this cuvette, which is filled with water, should have 0 absorbance. But you can see it does have a minor bit of absorbance. So let's get rid of that. Let's recalibrate our instrument. So I just tap on the screen. I tap calibrate. I skip the warm up because it's warm. It's been really warm in here actually. And then I finish the calibration. And then I click OK. And now, just like tearing a balance, 0 absorbance, more or less, to the 10,000th place. 1000th place, rather. Okay? So now we are ready for our experiment. Our blank, our cuvette with water in it, reads 0. And then we are going to measure the absorbance of our various solutions. So first up, solution A, which has a reading of, it'll stabilize pretty much immediately, just like a balance, 1.26 something. 1.2, it's a little jumpy today. Weird. Well, we'll just pick it. We'll just call it at some point. 1.2. 1.260. That's going to be our data point for A. 1.260. Okay? That's A. B. Should be half. It's half the concentration. 1.260. 0.625. 0.625. Now just a word on absorbance. Technically, Beer's law, the straight line that if you have more stuff, it absorbs more, only applies between absorbance values between 0.2 and 0.8. A equals 0.2 to 0.8. We just had a 1.26 for A, for solution A. Technically, it's out of the Beer's law range. However, for this lab, it works really, really, really well. So totally a valid data point for this lab. All right, 0.625 was our second data point for B. C should be half again, and look at that, 341. 341. That'll be our value. 341 for C. And D, last one that we know. Half of 0.341 should be around 0.15 something, or below Beer's law's technically valid range, but it still should work pretty well. And we're at 0.193. 194, 193, let's call it. 193. All right? Now, last but not least, we have our unknown. Let's use our eyeball spectrometers and see if we can figure out the concentration of this unknown. Let me get a piece of white paper. So here is our unknown. And with my blue glove, it makes it a little bit challenging. Here's D. I think our unknown is darker than D. Right? Unknown right here. D. Let's see. No, unknown's still darker than that. B. Our unknown might still be darker than that even. Let's go around B. A. Oh. It's a little bit less dark than A. So I think, using my eyeball spectrometers, that this unknown is between A and B. But it looks like it's closer to B and E. Yeah. Take the camera down. Just guys, maybe you can see it if I put it up close and personal. Here's A, unknown, B. A, unknown, B. Let's see what the spectrometer says. Unknown. Spectrometer says it is really, really, really close to B. It's actually between B and C. 0.555. Why not? Split the difference. 0.555 for our unknown. We're going to take our values for A, B, C, and D and learn to use, or practice using, if you already know how to use it, the graphing program, the spreadsheet program, Excel, Microsoft Excel. You can do it with a Google Sheet as well if you want a free program. But every CUNY student has access to Microsoft Office Suite for free, so you should download it and use it. Again, valuable job skill. We'll graph ABCD, get the straight line equation, and see where 0.555 for our unknown fits in, and calculate our concentration and see, is it B? Is it between B and C? But get it really, really, really exactly. And then your instructor can tell you, again, got a bunch of sample data, your instructor can tell you what your unknown is, and then you could see how far off you are.